So this work is led by Chujun Geng, a PhD student at Ohio State. Unfortunately, he couldn't be here due to visa issues. So IsoPredict is the first dynamic predictive analysis for detecting weak isolation bugs in data store applications. Let me say what I mean by data store applications. Or first, the motivation for the work is the data store applications are the foundation of today's service infrastructure due to their scalability, a few notes, I'm just remembering, fault tolerance, and ease of use. And so let me tell you a little bit about what we're envisioning here with sort of what we mean when we say data store applications. So data store application would consist of clients sending queries to a data store. This would generally be concurrent, and results would come back. So this could be like a traditional database with SQL queries. It could be a key value store and a key value distributed data store with key value queries. And results could be rows and columns or individual results. And the key point here is that these things are happening concurrently. So as an example, as a very simple example, suppose that we have an initial balance in some account of $0, and two clients are each performing operations to deposit money into that account, and one is depositing $5 and the other is depositing $3. So how would the operations look here? Well, not dealing specifically with SQL or key value, but just keeping in terms of reads and writes. To keep things general, client 1, its operations would read the value of the account into a local variable, add 5 to it, and then write that back. Client 2 would be similar, but it would add 3 using similar operations. So you can look at this probably and say, isn't there an atomicity problem here? Well, there sure is. And you can fix that with transactions, and a lot of these models provide transactions, and that's actually, we assume, a transactional model, and the programs are using transactions, issuing begin and end, or begin and commit transaction operations to the data store. So this actually, it seems like this program might work, and in an ideal world, this would actually work. An ideal world would be one in which data stores provide strong isolation or serializability, in which it's guaranteed that the execution will at least have the appearance of serial execution, in which transactions execute one after the other in isolation without interrupting each other. So one example of that would be where client 2 here, its read reads from the initial state, and then client 1 reads from the write by client 2. So this sort of seeming to, this is serial execution. The outcome here is going to be one where the final balance is $8. However, in the real world, data stores don't provide strong isolation. They don't provide serializability. They provide weaker consistency models like causal consistency or read committed. The reason they do this is for performance reasons and scalability reasons, to get much better performance and guarantees is why they provide these. But it means that under these weak isolation models, including this example in particular here, this execution can happen under both causal consistency and read committed, which are the two isolation models we looked at in this work. If both of the reads read from the initial balance of 0, then they're both going to write 5 and 3 respectively, and the final balance is going to be $3 or $5. So that's an unserializable execution. It has a result that isn't equivalent to any serial outcome. And the problem we address in this work is that we'd like to find these unserializable executions, because programmers generally aren't intending for this to happen, and they want to know about it. But the problem is, often this execution is what happens, both in testing and in deployment. So we'd like to be able to sort of look at these executions, but infer when these executions might have happened. So our problem statement, again, is to find these unserializable executions. Actually, by looking at the serializable executions is how we're going to do that. Although any mechanism would be fine for doing it. I'll show you related work now that sort of is various ways of finding these unserializable executions. This is an important problem, as others have shown, both because data stores are used so frequently and also because of this problem of unserializability violations, as many people have shown, is a really serious issue. And now I'll also try to motivate briefly that it's an unsolved problem, or not a fully solved problem. using testing can certainly be done to try to find these outcomes. The main problem here is that you'll often get serializable executions. You won't get the unserializable executions that we're trying to detect. Classical techniques like model checking, as we just saw in the last talk, and in static analysis certainly can be effective in this area, although model checking still suffers from scalability issues, and static analysis can have many false positives. There have been techniques that are well suited for or specifically targeted toward the data store application space. One is to sort of look for patterns in dynamic executions and infer from that executions that could have had a unserializable execution, but it turns out that there still are a lot of false positives in this prior work. There's also a technique from a few years ago called MonkeyDB that what it does is that each read tries to produce a read that is legal under the weak isolation model, and it does so by choosing randomly, and it's pretty good at coming up with individual executions, or coming up with executions that turn out to be unserializable. So it does require, however, a specialized data store in order to do that. You can't run this on existing data stores. So we looked at a different direction in this work. In particular, we looked at predictive analysis. So dynamic predictive analysis, what it does is it observes a serializable execution, and just based on observing that execution, not looking at the static program at all, it predicts an unserializable execution that could have executed. So there has been prior work on doing predictive analysis for shared memory programs, both for like finding data races and also for finding atomicity violations. There are some similarities here, but there was a key technical challenge that we had to overcome, which is that conflicting accesses are only partially ordered in these weakly isolated executions. So what that means essentially is there's many possible serialization orders, or also called commit orders, that can make an execution serializable. And you sort of have to check that every single one of those is, to ensure something's unserializable, you have to check that there's no commit order that actually exists for some execution. It actually means that checking whether a single execution is serializability or serializable is actually NP hard. And that makes it even harder to do prediction. It's sort of another step there where we're also predicting over all of the possible write-read orderings. And so this was sort of intractable for doing constraint solving, which I'll talk about shortly, but we use constraint solving to solve this problem. And so what we do instead is we use an approximation that works quite well in practice, where we encode a sufficient condition for unserializability instead. So that's all I'll say about this key technical insight of the paper, because it's a 15-minute talk, but I encourage you to take a look at the details. So the basic design of IsoPredict is what I'll discuss first, and then there'll be one problem that we'll have to solve as well before the full design. So again, we assume a data store here has multiple clients issuing queries to the data store. And what we did is we added an event recorder in there in order to collect the observed execution. And in theory, you could put it sort of between the data store and the clients and not modify either one. But we actually modified the data store, in this case, a specific data store. And the reason was we wanted to know for every read what its writer operation was, because our analysis relies on that. In theory, you could design the analysis so it could sort of be flexible with respect to what the actual writer of that was, or it could determine that in some way, but we didn't deal with that challenge in this work. So the event recorder captures the observed execution. It gives that to the prediction component of IsoPredict shown here. And what the prediction component does is it generates SMT constraints that basically say three things. Based on the observed execution, it should come up with a predicted execution that is feasible, that obeys the weak isolation level, like causally consistent, and that is unserializable. The SMT solver might say no such predicted execution exists, unsatisfiable, or it might say that an unserializable execution was predicted satisfiable. In that case, it can actually report what the execution was to the programmer. So here's that specific example, again, with the deposits of $5 and $3 by the two clients, and suppose that the observed execution is one in which the actual one that we saw before, the serializable one, in which client 2 reads from the initial state and client 1 reads from client 2's write. What the predicted execution prediction component would come up with is this predicted execution shown at the bottom. It would come up with the unserializable execution that we saw before, where they both read from the initial state. We'll report that to the programmer. So that works well enough for this example, but you might be wondering, do we have to worry about divergence? Do we need to worry about what if after some read, there's conditional behavior in the application that affects the rest of the application? And in fact, we do need to worry about that, and it does come up in a lot of the situations that we look at. Let's modify the example slightly. So, not slightly, let's modify it in a significant way so that client 2 here withdraws $3 rather than depositing $3. So the application code then would look different. It would read the balance, and then it would check to make sure that actually the balance is sufficient. If not, it will abort, which will actually cause this entire transaction to seem to not have occurred at all. The read and write events will not appear to have executed in that case. Otherwise, it will write 3 less than the existing balance. So suppose the serializable, we get a serializable execution when we actually observe it. And here, client 1 appears to go first. And then client 2, when it does the read from client 1's write, it sees that the balance is $5, and so it doesn't abort. It goes ahead and writes the updated balance of 2. The predicted execution that the prediction component of IsoPredict would come up with, if, as I've currently described it to you, is going to be one in which it will say, oh, well, they can both clients can read from the initial state. However, that execution is actually infeasible, because if client 2 reads from the initial state, it'll read the value 0, which is less than 3, and so it will abort. And so only client 1's transaction will execute, which is actually a serializable outcome, because that's the same as the outcome as if client 2 goes and then client 1. So this would be a false positive. We fix this by adding some more stuff to IsoPredict to get the full design. So I've just moved things up here to make room for other components. So we added 2 things. One was we wanted to make it so that things that came after reads in the execution would could be affected by that different read value, like conditionals, anything conditional on that value. And we don't know what that could be. It could be anything, so we're just conservative about that. That shouldn't be considered in the prediction. And we call those boundary constraints. We add those to the constraints. We can't still be sure, though, because of aborts could actually abort operations that have already occurred. And so to be more certain, we need to actually check that the execution can really occur. Also, this helps us sort of validate our technique's correctness, or our implementation's correctness. But the point in the design of why we want to actually try out these executions, is that an aborted transaction could mean that operations that in the past would actually not even appear in the execution, like we saw with the aborted execution. So instead of just reporting the execution, we try to so-called replay it. And we use this, we extend the recorder to actually try to replay this execution that occurred. Then we need to actually check that the resulting execution, which may still diverge, but in many cases we found, even though it diverged, it still led to an unserializable execution. So there was some change in the execution, but it wasn't large enough to affect whether it was unserializable or not. We would actually use the SMT solver to check whether the execution is serializable. And again, that's because it is an NP-hard problem to even check whether these weakly isolated executions are serializable or not. So we evaluated both the effectiveness and performance of IsoPredict. Not sure why I folded up my notes again. So we implemented IsoPredict's prediction and validation components. We actually extended the data store that was used in the MonkeyDB paper, and we also compared against their work as well. The methodology was that we used several OLTP benchmarks, and let me tell you just the takeaways of the evaluation in the interest of time. So for effectiveness, IsoPredict and MonkeyDB were comparably effective. Actually, they were both very effective on these applications at exposing these behaviors under causally committed and causally consistent and read committed. It'd be interesting to see what the outcomes were for programs where under these isolation levels, it was not so effective for at least one of these techniques. However, sort of qualitatively, IsoPredict is still more general than MonkeyDB because it doesn't require a specialized data store. And in future work, we'd like to explore how to actually make our technique work with any data store, sort of even in a deployed environment. For the performance, qualitatively, IsoPredict analyzes multiple executions at once, at least in essence, whereas only a single execution can be analyzed at a time by MonkeyDB. IsoPredict had long constraint generation and solving times. Actually, the constraint generation times were the longest, so that's also something to look into, largely as an implementation issue. So in summary, IsoPredict is the first predictive analysis for data store applications. In order to make this work and apply predictive analysis, we had to solve some challenges that were unique to data store applications. And as a result, there's a new way to find bugs in data store applications. Thank you.
We have time for some questions.
Hi, thank you for the talk. So you mentioned one of the challenges is sort of this exponential space of possible executions, and you're encoding these into an SMT solver. And traditionally, that's something that SMT solvers aren't very good at because you need to do some sort of symmetry breaking or partial order reduction as sort of as in the last talk. So I was wondering if you consider that, or if you do some sort of partial order reduction or symmetry breaking when you're encoding the constraints into the solver.
Right. In some sense, there's sort of two for-alls. There's the for-all over all the possible commit orders, and then there's the for-all over all the possible write-read operations. I guess what we do is we address all the possible commit orders by using the approximation that I briefly mentioned. But we address all the different write-read orders just by encoding that. And I think my understanding is that SMT solvers are potentially good at that part of it, I guess. That's sort of the magic of SMT solvers. But we are using the SMT solver as a black box.
Okay, thanks.
Very interesting talk. So fundamentally, you will try to run in read committed for performance. Now you're adding the SMT solver, a validation phase, and this validation phase is very similar to optimistic concurrency control for snapshot isolation or serializability. Now the fundamental question is, are you with that approach actually faster than just running in repeatable read, snapshot isolation or serializability?
I'm not sure I understand the question.
So fundamentally, you pitch the entire work with let's run in read committed instead of higher isolation levels for performance reasons. Now you're adding the SMP solver, event recording, replay, validation. Is it actually faster than running in serializability with elaborate strategies? So Postgres would run actually optimistically things concurrently, and then also report serializability conflicts and simply abort transactions whenever those bugs are detected.
So just to be clear, I mean, the SMT solver or the validation, that's sort of all offline. We don't assume that that's sort of happening on the critical path.
So how would you, okay, thanks for the comment. So if it's not on the critical path, how would you inform an application that there was actually a bug?
So we're not informing the application live, we're just informing the developers after the fact.
Okay, excellent, thanks.
Hey, thank you for this talk. So I had this question, like, do you try to track does this analysis basically work on a binary level, or it's more of a, like in the source programming language that you run on top of it?
Oh yeah, good question, but actually we don't look at the program at all.
Okay.
We actually, that's one of the keys to dynamic predictive analysis is you want to avoid looking at the program and just look at the execution of it and infer as much as you can just from that dynamic execution. So we're just looking at the queries and the results of those queries.
Okay, and like something can be done in these lines, like you attach hooks to some data library which does something like with the data store and data reads. Like, does something like that also work?
I'm not sure I understand. Are you saying sort of how would you implement this?
Yeah, like instead of looking at the complete program, like add hooks to these specific calls which do something with the data.
Yes, if I understand what you're saying, like in general, you could implement an analysis like this. You just need to hook into the queries and see sort of it's just the interface between the clients and the server data store that you need to sort of look at just that interface and see what goes across
Okay.
that interface, and that's the observed execution, if I understand your question.
Yeah, that's right. Okay, thank you.
Sure.
I had a quick question. So, have you thought about integrating application invariants into your model as a way of reducing constraint generation times? Because those invariants might, in fact, discard lots of constraints that you would otherwise have to consider.
Yeah, that's a good point. And also, actually, MongoDB didn't work by checking whether an execution was serializable or not. It actually checked application invariants. The one issue is that those have to be written, although they might already exist in some form. And yeah, it's interesting to think about some application constraints would be difficult to encode as SMT constraints, but
I was mostly as a way of reducing your constraint generation times because they
Right.
sort of constrain the space of things that you have to look at.
that's right,
So
that's
you have
right.
to generate constraints.
As long as you can sort of evaluate those
Yeah.
symbolically or something like that, you could do that. But I mean, the written languages like Python that are, difficult to analyze and so forth. So that we tried to sidestep that, but you definitely could do something like that.
Any other questions? If not, let's thank